still not completely known yet. And another laboratory allows us to study the Q systematic extreme happens on the sky. So I think you learned this from Kenji yesterday as well. The neutron star, the very dense object. So there we have the chance to look at the very cold but very dense Q-system matter. And I want to say that nowadays we are at a very good area trying to look into the Q-system matter on the extreme from these three aspects because of the advancement happens. For example, in the heavy inclination sector, now we are entering the precision frontier because you will have a lot of the high statistical measurement soon. You have the updates. For example, the detectors will also be upgraded, and in the non-productive calculation sector, because of the high-performance computing or the GPU usage, now we are also able to get a lot of more high statistical estimation for a lot of the system. Then in the neutron star sector, now we are entering the discovery frontier, and we will get a lot of the more advanced measurement from the gravity and the multi-messenger astronomy measurements. So basically, if we try to get some joint analysis over all these different aspects, we will get a more comprehensive knowledge or picture about the Q-system matter on the extreme. But because of the involved high complexity or some very data-hungry stuff inside those inside the computing within these different sectors, the modern computational paradigm from artificial intelligence, especially machine learning or deep learning, can actually enter our game to provide some practically powerful handle. And indeed, this has happened in a lot of other research already. This is just like the electricity in 100 years ago. Nowadays, the artificial intelligence, machine learning techniques is penetrating and transforming our everyday life, also from the industry to also the very forefront research aspects. For example, here, people are applying the machine learning, trying to make the mathematical, the knot theorem proven. And people also apply that in geoscience, trying to do the earthquake forecasting. And in high energy, actually, this is in particle physics, the machine learning application is already not a new stuff. So people applied that to do the signal identification, for example, for the Higgs discovery there. And this application is also very interesting to me, that people using this automatic differentiation technique in machine learning, trying to do the designing for the coil to perform very well nuclear fusion. And here, this is using the AI to do the protein folding properties predictions. So you already heard it from the media, I guess. So a lot of other stuff also happening. Sounds like very magic, but underlying those magic application, the engine for those techniques actually is deeply rooted in the combination of several facts and mathematical tricks. For example, a lot of the studies is using the deep neural network, which is basically providing us a very good function fitting procedure. So you can understand this deep neural network is a very universal function approximator. And this has been proven mathematically very well that the deep neural network, it can approximate any well-behaved mathematical function to any accuracy, provided you have enough neurons inside or enough layers. And another technique related is the differentiable programming strategy, which allow us to utilize, for example, the backward propagation and also the automatic differentiation later we will mention again, trying to get the representation here to be well optimized. So you have an efficient way to tune the parameters inside, even though the parameters here might be thousands of even millions of. So you don't need to worry about how to do this optimization. You have a lot of the well developed ways to do that. You can also put those optimization into the very modern computational devices like the GPU, which is quite fit doing such kind of a game. And just try to let us on the same page, I will also very briefly introduce what's the machine learning. So in a very basic entry into the very modern computational devices like the GPU, which is quite fit doing such kind of a game. And just try to let us on the same page, I will also very briefly introduce what's the machine learning. So in a very basic entry-level perspective, I already mentioned that we can understand the machine learning techniques is provide us a very good and pretty places. It might be this nice within the picture. It's a dog or cat, right? But we don't know what's the underlying mathematics on some training data set. And you also have some techniques telling you how to make the selection to be not biased to your training set. You have the testing data set to be separated. So basically, you have a way to pick the best functions out of your functional family. And then if you do the test, you find it's also working quite good in generalizing to a different situation. So that's it. So it's very simple, just doing this function fitting. And we also see that the four key concepts within the machine learning procedure is here. You have a model, you have a goodness, which is specified as a loss objective. You also have a way to do this optimization, how to activate. And for the data, you need to prepare the training set and testing set, trying to not bias, trying to not overfit into some of the specific details, right? So just these four components will allow you to perform this machine learning procedure. And here, for the model, it can be many different stuff. Neural network is fine. You can also use some other mathematical way, like the Gaussian process, or support vector machine, or even your ODE or PDE equations, or your model simulations. So once you know how to evaluate some loss functions over that, and once you know how to perform the optimization, trying to pick up the best one, then you can also replace the model to be your ODE equations or PDE equations. And suppose we are using this deep neural network, which is quite popular in machine learning, to be the model here. The deep neural network basically is composing many very simple building blocks. And for each of these building blocks, people call it a layer. It's just doing a linear transformation plus some nonlinear activation function. And this compositionality allows such a structured calculation to be able to perform some hierarchical learning. Hierarchical means usually you will find a learned neural network, it will use its forefront layers to just perform some very simple pattern recognition, like if it's for image recognition, it will try to do the very simple edge or the very simple lines representation, and later gradually it will combine those simple patterns into more complicated stuff. So very similar to our physics concept, right? So like we can always use the hierarchical way to decompose different physical model or systems into different effective degree freedom. And here similarly, and in the end, for example, if we're doing an image recognition, suppose this is trying to recognize a handwritten digits, this recognition would be similar to in statistical physics when we try to calculate all the parameters of a field system for this statistical system, right? So essentially, we need to find a way trying to integrate out not processing. It's also trying to get rid of those non-abstract, those higher order noisy information, the high frequent part. And in this sense, people have a guess that the training or the learning of this neural network might be similar to the RG procedure in physics as well. And another point I want to deliver is, suppose we are using this kind of convolutional neural network. So you have the convolutional kernels to be involved in performing such a kind of deep neural network learning. It's including some invariance as well, like the translational invariance and the locality information is naturally embedded inside such a convolutional neural network, the training procedure. And this is also related to physics, like if you want to do some analysis and you know there are some symmetries, some invariance should be there, then by encoding, by explicitly let those invariants to appear inside your analysis, might let the whole process to be much easier. So here, similarly.
Before you go on,
yeah.
About this graph, the top, so the W represents a linear map?
Yes, the W is the matrix multiplication coefficient.
And the blue is the activation function?
For each of the nodes, it will first perform such a linear transformation, then you apply a non-linear activation function for this output. And in the end, this layer, you can understand it as a whole to be a building block. It's performing a vector-to-vector operation. But it's non-linear in the end.
So the circles represent this non-linear map?
Yes, yes. Yes. And you can have different activation functions, and you can have different, in the end, you will design some loss objective trying to perform your task, and have different architecture as well. Here, this is only a very simple feed-forward architecture. Like if you purposely introduce some parameter sharing mechanism, so convolutional neural network is having this parameter sharing is you try to let your whole weight matrix to be sparse. But how to introduce this sparsity depending on your problem, like you know there are some shared mechanism should be there that's reflecting the locality or reflecting the translational invariance, then you purposely introduce that part. That can make the whole calculation to be easier.
That would reduce the number of lines in this W1 map? Or is that would that be the idea?
Yes, that's changing this big W1 matrix to be a very sparse matrix. Yeah. Okay, then another point I should say is machine learning or deep learning is not only about function fitting. So in a probabilistic perspective, there are actually two different kinds of task or learning models. So one is this discriminative learning, and this is usually done in a supervised manner. In the end, the final purpose is trying to do some prediction. What you're really learning is learning some conditional probabilities, so P of y given x. So theta is the parameters of your model. This can be neural network, can also be some other models. And once you learn this conditional probability, you can do predictions on some unseen situations, like you input a new stuff, x, you try to get the corresponding output for that. So that's very similar to the function fitting stuff we mentioned. But there's also another task called generative modeling. In a probabilistic language, where basically this joint probability distribution in unsupervised manner. You do not know what's the label related to this x. You only have a collection of those observable or measurement. You try to figure out what's the structure of this system, create some new examples out of your learned joint distribution. So you can do some synthesis for image creation. And if this is a statistical system, then you are able to sample a new configuration, a new field configurations, right? So that can help you to do this partition function estimation numerically. And actually, Feynman has a famous quoting saying, "What I cannot create, I do not understand." That's kind of motivating that once you have the ability to generate new stuff following the same, you will be clear as well. So if we try to force the learning algorithm to be able to generate this new configuration, new examples out of the same statistical distribution, then the model is also able to figure out what's the internal structures of the system, trying to figure out what's the organization and what kind of effective degree of freedom that you can align, that you can assign to the system, right? So basically, our lecture will be separated into two parts. One is utilizing the discriminative learning strategy, trying to solve inverse problems involved in heavy equation physics. And in the afternoon, we will mention some generative models application in physics in general.
Can I just, this would be, the generative model would be, if I give you random data, random initial conditions, you tell me, you produce
a new one
that looks like heavy ions.
Yes, yes. If we can provide a lot of the heavy equation measurements, and we suppose this is following the same distribution, then we can learn this distribution using this random collection of the measurements and try to generate a new measurement. So basically, you get this joint distribution with your model as well. So you're using this neural network to provide the parameters for some distribution, or directly learn this mapping from some simple distribution to this complicated distribution. Yeah. We will mention this in the afternoon. So if you have any questions, you can interrupt me at any time. And then we mentioned the differentiable programming strategy, which will be used to perform the optimization. Basically, this is just a fancy name to the application of chain rule in calculating the derivatives. So we can imagine our computational graph, the neural network, or any kind of the model construction might be complicated, but in the end, you can always form parameters and go forward until some objective. And usually this objective is a scalar numbered loss stuff. You try to measure how close or how different this would be for your calculation to a desired stuff. And we care the adjustment to the parameters, trying to let this objective to be as small as possible. So you need to calculate the partial L over partial theta. And this can be easily done by applying the chain rule, right? So partial L over partial theta is when you apply the chain rule to all the intermediate variables, it's just here. And this kind of, people call it automatic differentiation strategy to perform this chain rule. So this evaluation is proven to be much more advantageous compared to the numerical differentiation or even the symbolic derivative calculation, and it can guarantee the machinery precision always. And the essence is we always starting from this is the end calculation, right? So you're first calculating partial L over partial this capital Tn. The Tn is the last node within your, and each of those multiplication basically is a vector to Jacobian calculation. So you see all these intermediate factors, the partial Tn over partial Tn minus 1, this is just the linear response for one of the operation nodes in between, right? So you know what's the response if you change a little bit your input and the induced change in the output. That's the Jacobian matrix. And this chain rule calculation, you just understand it as repeating this vector multiply Jacobian matrix. And trying to make the coding to be easy, people usually introduce such adjoint variables. This adjoint variables is defined as the partial L, the final objective, with respect to partial t, the output of one of these computational graph. And in the end, this kind of the backward propagation for performing this chain rule is just multiplying these adjoint variables starting from the very end all the way backward to any of the parameters or nodes that you cared. And if your computational graph is quite complicated with branches inside, then this backward propagation is also easy. You just need to find out the contribution from all the child. So here, if you do the forward calculation, you can think of this as the parents and this is the child nodes. And if you want to do the backward propagation, trying to collect the feedback information, what kind of changes have been induced by those parents changes, you just sum them up. So very natural, right? So this is the chain rule application. And I want to mention again that such kind of automatic differentiation strategy can also be applied to our physical model simulation as well, if you want to do some inverse designing or inverse fitting. So once we know how to provide, how to calculate such kind of adjoint variables, then you just apply the chain rule in this way. You can easily do this optimization for that on GPUs even. Good. So that's 3 slides. It's just a very brief introduction to the machine learning related jargons or the very essential techniques. And what I want to talk today in this morning is about how we are utilizing these machine learning techniques in solving the inverse problems related QCD matter exploration on extreme. And from our experiences, we basically have used such 3 different approaches. So by the way, the inverse problem is a quite general technical challenge in a lot of the scientific disciplines. There, suppose we have some quantity of interest or some causal stuff or our physical information. We know how to convert those stuff into their corresponding outcome or the corresponding measurement. So we have the well-established, whatever, the physical model simulation or the explicit forward mapping. Just we care about, given the measurements, given the corresponding outcome, how we can make inference about their causal information, about those physical quantities. This mapping exists, but might be very implicit. Or in some cases, if our measurement is very noisy, then such an inverse mapping is degenerated, it's ill-defined. So you have different solutions related. So how would you find a way to solve it? Find the corresponding causal information. So this is the inverse problem. And utilizing machine learning, we can do it from such 3 different angles. The first is use our known explicit forward mapping to prepare a lot of the training data in a date-driven manner. You try to learn this inverse mapping directly. So this is called the supervised inverse mapping calculation. And the second way is quite familiar to everyone. So just perform the normal statistical chi-square fitting, but you can introduce the Bayesian statistics. You try to sample out of this posterior distribution of your physical causal information given your final observables. And I just want Bayesian inference is also involving some machine learning models. Like for this, if you want to have a very efficient parameter space searching, you want your forward mapping calculation to be also very efficient. Sometimes you will introduce some emulator to replace it. The emulator will provide you a very fast translation out of this physical quantity of interest, how to translate it very quickly into the corresponding outcome. Then the third way is what I mentioned, using this automatic differentiation explicitly. So this is also trying to fuse our physical prior information with the whole inference procedure as well. So we can apply the chain rule we mentioned in last slides, trying to tune the parameters inside. And here, these parameters might be the parameters within the neural network to represent this physical quantity. And it can also be we are replacing this explicit forward bias network. So this is trying to introduce a neural network emulator for our physical models. And in the end, we care what kind of input or what kind of causal information is inducing such a consequence, right? So you apply the chain rule, this automatic differentiation, to tune the parameters involved. So in following, I will introduce several projects related to these different approaches to address the inverse problem. So first, this is applying such kind of machine learning related techniques in learning the physics related to heavy anculations. And we mentioned already that heavy ancylation is colliding to trying to achieve the very extreme conditions to excite the nuclear matter to the new state. We call it quark-gluon plasma, right? And the challenge being involved here is maybe indeed those deconfinement is happening, but it's only happening in the early stage. So the created fireball will undergo a very rapid expansion and cooling down. So the temperature will drop out very fastly. So to some point, it will hadronize again into the hadronic particles. In the end, from the experimental detector, we can only get access to those finally emitted hadrons or their decay products. So we can record their mass or the PID. We know how to identify each of the particles and also the momentum distribution. But we get no direct access to those early stage information, those interesting physics happened duration, right? So this is what we cared. And another very important challenge is even within our modern, our state-of-the-art physical description for the collision dynamics, there are a lot of physical uncertainties to be involved. For example, the initial state fluctuation, the Qcd matters, bulk property, their transport properties, and also within our model, we have different set of parameters. For example, the switching temperature between the hydro to the hadronic cascade. So all those different parameters is having some entanglement influence to different kind of consequence, our measurement in the end. So you can think about those measurements to be a smell out of this cooked, very hot soup. In the end, we try to know some knowledge about this hot soup, what's the ingredient, what kind of physics happens for this hot soup, but you only get a smell. And the smell is influenced by many different uncertain factors. We call it uncertain because currently from theoretical point of view, we actually do not have 100% complete knowledge yet to them. Whatever from the lattice calculation or from differentiations, we have different, not converging results yet, right? So the question is how we can disentangle those different factors, trying to, for example, reveal some fundamental physics or some of the cared physics factors in inside. This is not possible yet. And of course, you can have the two different strategies was mentioned in the last slides. You have three different approaches. And usually in such a business, people apply either the Bayesian inference or what we started is utilizing the deep learning, trying to get this inversion mapping directly. So we will mention both of these two approaches to this business in following. And if we use this deep neural network strategy, basically is trying to learn such an inversion mapping out of your final measurement. Because, by the way, so the problem itself can be easily formulated as an inverse problem because given all, including initial state, equation of state, each over S, different parameters, you are having the setups within your model simulations. We have our simulation to convert them into the corresponding final state information. The final state means this is the experimental detector's output in our heavy anculations, right? But this inversion mapping, we do not know how to formulate. So this is similar to the image recognition that even though we all all having such an ability to recognize what's the content within the image, don't know how to write down some explicit math. But in computer vision, nowadays, people are utilizing this supervised learning to get this mapping directly in the big data sense. You provide lots of the labeled network to capture what kind of math can help you to recognize what's the content inside the image. So similarly, we propose to use convolutional neural network trying to learn or trying to let this to recognize what kind of physics happens from just looking at the final state information of the heavy. But if we want to copy such a procedure, we need to provide some labeled data to that, right? Some training data with the corresponding the outcome information that you wanted to output for you, right? And this can be done by invoking state-of-the-art event-by-event hydrodynamic simulation. So we utilize a package to provide the training set, and there we can manually set in some of our cared physics. So here we cared first, and the starting point, we try to let the network to learn what kind of QCD transition type has been involved in this heavy collision dynamics. So it's either crossover or first order phase transition. So those are all included inside the equation of state that you have been using in your hydrodynamic simulations, right? And you know what's the corresponding outcome that you want to have, and you also record the final state information. So here we're using the final state, the pions spectrum, their PT and the transverse angle distribution. And this is very image as well. It's a matrix. Basically, whatever the image or here the final state pi spectra to the computer is just one matrix. You try to let the neural network to analyze this matrix, trying to get you what kind of information has been involved inside the whole simulation. So this is a supervised learning problem. We utilize the neural network trying to capture this inversion mapping directly from a big data, from the training set that we can provide. Yeah.
So somehow this involves trust in the model of the hydrodynamic code. I mean, especially first order simulation, somehow that you trust that this thing is accurately reproducing. Right? I mean, so especially when it comes to ions, I don't think that, I trust the hydro so much.
Exactly, you are right. So we are assuming the hydro is the right model in converting those information to the outcome. So, but even on this level, we do not know how to make such an explicit inversion. So that's a starting point. Even though maybe physically those assumptions many people are not believing, that's fine. But we want to ask the question.
Within this model.
Yeah, within such a dynamics, it's a hydrodynamics. If there's such kind of transition happens, how would you be able to recognize it by looking at only the final state information? That's our setup. Why the what is?
Yeah, what is the point to use the CN?
Image-like data. And CNN has been proven to be very good at recognizing patterns within such tensor structure data. So you have the convolution operation.
You have I think that this is not a 2D, but a multi-dimensional image, right?
2D, two-dimensional. So this is the histogram of the particles along with the PT and phi. Histogram. So that's spectral. Well, yeah, we're only using the momentum information.
The 2D image in what space?
In PT, so one axis is PT, one axis is phi. Angle, transverse angle. So. And you're doing the histogram over this space, you get the picture, you get a matrix. Yes, usually we only see the plot of the integrated spectra. For example, you integrate over the phi, you will have the PT spectra. Then it's a one-dimensional distribution. But in principle, this information is there. But anyhow, this is our setup. First, we assume we can get access of those 2D spectra to see if it's possible to get this recognition ability out of such a hydrodynamics.
And does the convolution neural network need to build in things like, azimuthal, like if they change pi plus pi plus 2 pi, I should have the same
yes
periodicity, and also the fact that PT can't be negative.
PT is always positive.
Right.
That's the PT.
So do you have to build that into them?
Yes. That's prepared inside your training set. You prepare your input image to be the PT and the phi spectra. And I see a point. I mean, do we need to tell the neural network what kind of PT beings you have been using? This is explicitly set in. So you always use the same PT beings for the whole training set preparation and also for the later testing, for the checking. Yeah, before going on, one thing I want to mention is we need to be aware that such a problem setup might be problematic because we know the neural network will anyhow give you a prediction per training. So after training, you always get some prediction numbers. It's the probability that the network thinks it's a crossover of first order. You always can get a number if you give it a new input event. So, and why I say this might be problematic because it might be the case that the whole evolution might wash out all those information related to this transition dynamic. This could be, and even in that case, the network still is able to give you some predictions. So we need to be very careful in making the conclusion in the end, and we need to do very careful testing, separate testing. So you need to, in the end, give it some program divided this event. So for every event, it's a normalized spectrum. And so I mentioned that for the testing, we provided different setups in our simulation. Like we vary the initial state, we vary the shear viscosity values, we even vary the simulation package that we have. And we see that on these two plots, each line is representing one collision event, and the two colors, either red or black, this is representing its transition type. It's using a crossover equation of state or with a first order phase transition equation of state. And we see utilizing the traditional or the conventional observables. So this is the PT spectrum. So integrate this spectrum, this 2-dimensional spectrum over the phi, you get this PT distribution. And here, this is the V2 elliptic flow as function of the PT. So utilizing these two conventional observables is definitely not able to recognize what's the corresponding phase transition has been involved. You have a quite large overlap between the two different cases. It's either crossover or first order phase transition. But utilizing our trained convolutional neural network, I will not talk about the details about the structures here. Basically, it's a convolutional neural network. And in the end, on this testing, by calling it testing means involved inside the training. So it's a separately prepared collision event. So we have above 90% classification, and it's an event-by-event classification accuracy. So for each event, it knows has been involved inside the simulation of this event. So compared to these two cases, there's quite large overlapping. Definitely, we succeeded in classifying what kind of transition has been used. And so this classification performance ability is robust to these initial conditions or the different values for each of S, because inside this training set, we purposely change it for these generations. The first conclusion we can make is we know that at least for our used hydrodynamic setup, information about the early time QCD transition, those information is still contained in final stage of pion spectrum, because otherwise, for this testing, we cannot get such a classification ability. And with the trained convolutional neural network in a supervised manner, we are able to decode this information back. So all this conclusion, to be safe, this is only on the hydrodynamic level. So if we only consider a hydrodynamic, and within such a dynamics, we ask the question, what if we still be able to recognize the transition dynamics happened in early time from looking at the final state? So it's possible within such a setup. Good.
So you have all these is sensitive to, we said it's event by event, right?
Event by event.
So somehow measuring, it can't really, it's measuring all the particles, right?
That's true. That's true. So this is assuming perfect statistics for the pions. Of course, in reality, you always have the detector efficiency or different cut, right? Yeah, that's also our next slides want to deliver it. So we further deepen such a strategy into more realistic situation. For example, including so this is including the afterburner hadronic cascade effect. So we open the ULQMD simulation for the hydrogenerated distribution. So this is taking into account the finite statistics and also some stochasticity effects there. And in the end, it's also able to recognize what kind of transition type is there for such an event generation. And later, we also put the same idea into a non-equilibrium transition simulation, basically asking if it's possible to recognize there are baryon clamping induced by the spinodal dynamics or not. But in the end, the classification ability is reduced a lot, but in the end, it's still larger than random guess. Random guess means you have 50% accuracy, but here we can get around 60%. Means on a large ensemble events, you are able to recognize what kind of non-equilibrium transition has been using here. And here, later, we also included the detector effects. We know that from the detector, essentially, we're only recording the particles' momentum information, their mass and charges. It's in principle a point cloud structure. Later, I will mention this again. Diagram to represent one event. It might be very sparse because you have the detector efficiency. You also have a lot of the COT introduced. So you do not have the perfect statistics. And in this case, the point cloud network is the proper network structure, trying to respect the permutation invariance. Permutation means if you change the orders of two particles within your record, it's still the same events. So utilizing the point net to be our model, we showed that it's also able to recognize the transition types being involved in your simulation. And basically from those efforts, we're just trying to construct a bridge between the experimental result to our theory models, trying to give you a way to quickly and efficiently make the knowledge extracted from the measurements. So this is utilizing the supervised learning way to learn the inversion mapping directly. And the same kind of idea is also applied to, so here this is to detect the chiromagnetic effect. It's a collaboration with Xu Guang and his student Yuan Sheng. And basically, we input the collision events generated from AMPT. And these events have two different classes. One is with the charge separation, one is without the charge separation, trying to see if the network is able to learn such a classification ability on these two different kinds. Of course, in the end, we need to carefully check it into some realistic case. So at least from the EMPT simulation perspective, we are able to make the classification on different on-scene events and trying to see what the network has really learned. We call it a deep dream technique. Basically, you tune the input to this network. The input is, again, the histogram of the pions for each of the events. Their PT and the phi distribution. Basically, this is the PX, PY distribution. So you tune the input, you make a variational change to this input, trying to see what kind of input can let the network give you 100% sure that this is with the CME, having this charge separation. In the end, by the automatic differentiation strategy, we can perform such a variation. The network gives us such a input it should be. So you have some separation patterns, but meanwhile you also have such a which is a little bit not so easy to understand. And on the right, this is applying similar strategy, trying to identify the phase orders happened for some non-equilibrium to simulate a scalar. This is the sigma field evolution, which is mimicking a very simple Havan-Clayton phase transition. And we want to know to which extent we can classify the phase transitions as either first order or crossover that you have been introduced into your long-term simulation, basically contained within your potential terms. And in the end, this we find if you are controlling these noise terms, you are able to make the classification to be very well. This is representing how good it is in classifying these two different phase orders. But later, if you increase the noise terms, the classification ability is decreasing, but still, on an average perspective, you are still able to recognize such different collision events as belonging to the crossover or first order. And as another trial, we did such a recognition task, trying to make the prediction for the used damping coefficients that you have been using in the long-run dynamics. Basically, we want to know by looking at only the final episode, the final stage of this simulation, if it's able to make again what's the involved dynamical parameters for this dynamics. And here, for this long-run simulation, we care the damping coefficient. So the prediction is not perfect, but reasonable. You can use such an R square, which is the determinant of coefficient, to represent the performance. It's above 90%, above 0.9. And I want to mention that all those performance plotting is for the on-scene collision events simulations, not used inside your training. So you know that this is generalized well to different situations. And then I mentioned that if we want to consider the output from the detector, essentially we're having the point cloud structured records. Point cloud means we need to record each event using a list of this particles information. So each row is representing one particle, and each column is representing some characteristics that we are having from the experiment measurements. So here we just use the momentum to be their characteristic information. So basically, from the detector, it's not the heats or the tracks for each particles. And we wonder if we can build such a bridging model trying to translate the final measurement from the experiment to the corresponding physics happened for such a collision dynamics. And we are utilizing such a point net to be our model, we mentioned already. And the good point for the point net is this can respect this order invariance of this point cloud record. Order invariance means if you change the orders of from this. If you can explicitly make such a permutation invariance to be there within your model, you can more efficiently to capture the collective structure of such an event. And we apply the PointNet model to do the impact parameter estimation for CBM experiment. CBM is one scheduled program in FAIR and GSI. CBM is the compressed baryonic matter. The physical goal is trying to understand the properties of Qcd matter in the very high density region. And one very important feature for such a experimental program for the CBM is it will have a very high event rate, and basically per second you will generate, well, hello? Sorry. Hello? Good. So there you will generate roughly 1 terabyte raw data per second in the CBM experiment to be processed online. So we really care some very efficient online event characterization models, or how to select the useful data, how to select the useful events to be stored or to be analyzed further. And this kind of point cloud network allow us to do some event characterization. So as a demonstration, we showed it can very quickly do the impact parameter estimation, so which is one essential information for the event geometry. Because later, if you want to do the critical endpoint searching, you need to have which as well, right? So such event geometry analysis needs to be done online in a real-time perspective, and we demonstrated how to perform that using this point cloud network. And in the end, the precision of those estimations based upon the URQMD simulation is quite good. And of course, we also applied the similar strategy to the phase transition type classification as well, similar to what we mentioned on the hydrodynamic simulation study. Just here, we replaced the hydrodynamic simulation to the URQMD simulation, which is the proper model people believed that can fit into such a low energy heavy collisions. And similar networks, similar network structures, the point cloud network is also applied in classifying what kind of collision systems it is. This is a work done, collaborated with she's also sitting here. Basically, we care. Nowadays, we know that the small system at the P-led collisions and the LED-led, the peripheral collisions, if they have similar multiplicities, the other velocity stuff, but we want to know if those velocities, if those viscosities region are really the same, or you can have some distinct characteristics. So we train such a point cloud network trying to classify for similar multiplicity events, it's from a small system or from a larger system. And the results are quite promising, at least for the case that we apply that to the full momentum point cloud, means we provide all the information related to this event. But purposely, we're also trying to handle some information for this point cloud, like we only provide the transverse momentum information, or we make a random rotation to the events to see if it's due for large system. If you're interested, you can go to check with our people online. Good. So all above is using this supervised manner, trying to capture the mapping directly. So I mentioned there's also another popular strategy is doing this statistical chi-square fitting, so utilizing the Bayesian statistics. And this is quite a large company already nowadays, like Duke University. They apply it to the heavy collision physics analysis, and they published many papers, including in Nature Physics. So the basic procedure for performing a Bayesian statistical inference is here. So provide a lot of the model simulation with different model parameters that you care. And in their analysis, they choose the torrential initial condition and the event-by-event viscous hydrosimulation to be there. For the parameters, they try to make the adjustment, including this initial state and the switching temperature and the temperature-dependent shear viscosity and bulk viscosity, and trying to make the parameter searching to be efficient. I mentioned you better to introduce some very fast translation. So this is done by utilizing the Gaussian process, which is a very traditional machine learning model to be the emulator here. Basically, Gaussian process is trying to make the prediction utilizing a Gaussian-like distribution, but it's an infinite dimensional Gaussian distribution. And you will learn a mean function and a covariance matrix functions. In the end, all those information is contained in this data set. The training set is provided from your real model simulation. And this is just performing a nonlinear interpolation. So you have a nonlinear interpolation to do the translation later inside your parameter space searching. And once you have such a fast emulator, you just encode it inside, for example, people are usually using this the Markov chain Monte Carlo parameter space searching. Basically, you make some random change of your parameters inside your very big dimensional parameter space and trying to calculate the probability to accept it or reject it. And that probability is utilizing the posterior distribution, the P theta of D. Theta is your parameter you want to tune. D is the evidence, the final measurement. And this is just applying the Bayesian rule. You calculate the likelihood for each of the parameter choices chance, and you also make some prior distribution over those parameters and use that to be the acceptance or the rejection guidance inside this MCMC calculation. And in the end, you can get a lot of the examples from this posterior distribution. Then you make the statistical average, so you can calculate their mean values and also their correlations between each other for the parameters. And on the right, you see they're analyzing the inference results for those different parameters, including the initial state and the dependent shear viscosity. And once your mean distribution on this diagonal line is having some peak, that means this parameters is having some very crucial influence to this chosen evidence, to the. If it's very broad, that means the influence is not well captured by such a process. Also, Bayesian inference to reconstruct the density-dependent equation of state for the low to intermediate collision energies measurement. And for those collision energies, we know that the interpenetration time for the two colliding heavy nuclei might be very long. So the compression phase and the hadronic cascade effect is dominating the stuff. And for such a low collision energies, the normal hydrodynamic simulation might lose its validity at the moment. People are not yet there. So we utilize the URQMD to be our physical model to translate from the model from this density-dependent equation of state to their corresponding final state information. And for the final state, we choose this protons elliptic flow as function of this collision energy and their mean transverse kinetic energy. So know that the elliptic flow, this is sensitive to the equation of state because it can reflect the expansion effect, right? Similar to this mean transverse kinetic energy. But essentially, the stiffness information can be encoded inside the mean transverse kinetic energy for protons. So we utilize the measurements here for protons to be the evidence, and we also augment our URQMD simulation to be able to incorporate any kind of density-dependent equation of state, utilizing very similar to a mean field treatment. You introduce a density-dependent potential terms, let it enter your equation of motion for each of the particles, and for those density-dependent potential, we are utilizing a parameterization with 7 parameters. You see that here we randomly select the numbers for these 7 parameters. You have different density dependencies. And given this density dependency, you can easily convert it into the corresponding equation of state. And we want to know how to tune the parameters here to let our simulation to accommodate these 2 measurements. And again, we roughly estimated that if you want to do such a parameter space searching, which is 7-dimensional, and trying to calculate the corresponding observable of protons V2 and mean transverse kinetic energy, you really need a huge computational resources. Even though for each parameters, for example, if you only care 10 different values, that's a 10 million parameters conversion. And for each of those conversion, you need to calculate really a proper statistics for each of the data point here. So in the end, it will be several decades you need to do this very brute force searching. So we need to introduce a fast emulator. Again, we're using this Gaussian process, trying to convert the corresponding 7 parameters to their observables. And those plots are showing us the performance of the learned Gaussian process. We just provided 200 different 7 parameter setups, and those 200 different setups is utilizing some very general physical guidance. You try to let the equation of state to be causal, not violating the speed of sound is larger than 1. And also we constrained the low density part to be, this is using a chiral mean field calculation to fix it. Basically, you can constrain it using any of your preferences. For example, this can be constrained from the very low energy nuclear experiment, or utilizing the chiral effective theory. You know how to constrain the very low density part. We only care the variation, the inference over 2 to 4, or this is 4 or 5, of course, times the saturation densities equation of state. Good. So with the emulation well constructed, we can perform this posterior distribution sampling, which is proportional to the likelihood times the prior I mentioned already. The likelihood is telling us the chance that such a parameter setup can accommodate the already happened fact. The fact means the evidence, the observables that you have from the experiment. And for the prior, we just use a very general uniform distribution for the parameters to not introduce any bias for that. And to validate our pipeline for such an inference, we first perform some mock test or closure test. There you can randomly or manually to set in some density dependency for your potentials that will correspond to some density dependent equation of state. And you put it into your model simulation, get their corresponding observables, and suppose those observables are the evidence to see if your pipeline is able to reconstruct what kind of equation of state you have been using. So trying to validate this. Here, these 4 plots are showing us the reconstruction performance. Basically, the solid blank curve are the used, we call it true, the used density dependent potential terms. And the color, the 2 dashed curves are the reconstruction for their mean value. And the MAP means we only select the maximum posterior distribution related curves. And those bands are representing their 2 sigma confidential region. So we see that it's reproducing quite well the manually setting equation of state for different cases. So the upper rows and the bottom rows, they are using 2 different equation of state. And on the left and on the right, the difference is, suppose we remove 2 evidence points. Suppose we remove the very low energies, mean transverse kinetic energy. So what will change for our reconstruction sensitivity of such an inference pipeline? And we see that indeed there are some influence on the quite high density region, but to the, at least from 2 to 4 times saturation density, within our closure test, we didn't see a lot of the differences if we remove 2 points for the mean transverse kinetic energy inside our model simulations. Because later, when we try to apply such a pipeline into the realistic measurements, we observed some deviations. So here, we apply such an inference pipeline into the real experiment measurement. And on the upper panel, this is utilizing, we call it 15 data points, means all the measured protons V2 and the mean transverse kinetic energy, 15 data points are used as the evidence. Then the inferred equation of state, the density-dependent potential looks like here. So it's a quite stiff equation of state happening. But if we remove these 2 points, the reason we remove these 2 points is this is happened quite a long time ago compared to other data points. And also, obviously, we see the magnitude a little bit higher than others if we consider. So once we remove these 2 points, the inference is becoming softer in such a region, might indicating some phase transition, first order phase transition, but we do not know what's the real reason. At least this is a result from our Bayesian inference. And this is also pointing to the tension between measurement for the very low energy part, and this is from 5 GeV square root collisions. So means in future, we need to put more efforts in getting high statistical measurements in this region, which is promising to, for example, in HIAF or in CBM and FAIR. And another reason might be tension in our model description for the physics happened here. So this could also be, so we also need to put some efforts in polishing, in improving our model simulation there. Because in such a model simulation, we only introduce explicitly the density dependency for this evolution, but didn't put the momentum-dependent interaction explicitly in. So this is a quite topic on the debate, how to properly set in the momentum-dependent interaction into the hadronic cascade. Anyhow, this is the inferred results for the density-dependent equation of state. If you convert them into the speed of sound, it looks like here. The 2 bands, one is the red color corresponding to the case here, and one is this black inference results here. And this blue band is just for comparison. This is one inference from the neutron star observations. So interesting point is they both show, at least for this 15 data point scenario, there is a peak structure appearing, might be related to conformality broken that mentioned by Kenji yesterday. And but for this 13 data point scenario, the speed of sound is having a deep structure. So if this is true, this is an indicator for the first order phase transition. So we need to look more carefully into the business there. And another point is we checked the predict of the inferred equation of state in making predictions for different observables. So here, the 2 colored curves shows the URQMD prediction utilizing such a density-dependent equation of state for the V1, the directed flow as the dV1 over dy compared to the data. So we see it's predicting quite well, or let's say reasonably fitting to the data. And to be noticed, those measurements are not used inside our Bayesian inference, meaning the inferred equation of state can reasonably describe also the measurement here. Good. If no questions, we can go on. So further applied such a Bayesian strategy in imaging the nuclear structure in isobar collisions. You may heard that nowadays people are using the high energy heavy collision to be a way to study the nuclear structure, try to get knowledge about, for example, the nuclear deformation parameters or the neutron gain, different stuff, which is usually done by the low energy, the nuclear experiment. But here we care how to relate those initial state their final state measurements. This can be formed as an inverse problems as well, right? So Bayesian inference can be naturally applied. But here as a very simple demonstration, we suppose the conversion is utilizing Monte Carlo global modeling to translate the initial stage nuclear structures parameters, including their A, their R, and the bit 2, bit 3, the deformation parameters, to their corresponding multiplicity information. This is the eccentricity, the epsilon 2, epsilon 3, and the D perp means this is correlated to the mean transverse kinetic energy part. And we asked the question that if those encoding of those information within those final stage information can be done on single system or not first. And the other question is, if you want to do a simultaneous inference for the isobor system with only the ratio, if it's possible, utilizing this Bayesian inference. And this is the two questions we're asking this analysis. And in the end, it turns out for the single system, this can be easily done. But a caveat is, again, there are model dependency because we only assumed a very simple Monte Carlo global conversion. And now we are also progressing with, collaborating with Guo Liang, trying to utilize the AMPT simulation conversion to see if it's still able to convert back information about the nuclear structure parameters out of those final state information. And this two plot shows you the Bayesian reconstruction results for the single collation system for either this rosenium or the zirconium collations. And we also find that if you provide information for the multiplicity distribution, this observable alone can already do a quite good job in reconstructing back the nuclear deformation parameters. But if you only provide other informations without this multiplicity, it will very hardly to recognize the corresponding parameters for the initial state. And then we performed the simultaneous fitting utilizing only the ratio. In the end, the result is also quite bad. And the only severe is also from the single system's multiplicity. This is something we are a little bit surprising. So means if you provide the ratio of those four final state information to a Bayesian inference, it's very hard to get the initial nuclear structure information out. But if you can provide the single collation system's multiplicity distribution, then this reconstruction would be possible. So for more detailed information, I suggest you to look into the results and their analysis in our paper here. Good. Now, what's the time? Sorry. Let me use another 10 or 15 minutes trying to deliver information about. We also have a third strategy. It's utilizing the automatic differentiation, trying to get this inverse problem to be addressed. And I use this case to demonstrate to you how to do that. So here we care about the in-medium heavy quark interactions. So object is bothmonium, the bond state of B and B bar quarks. And because of their large mass and a relative small velocity, we can have a non-relativistic description for such a system. And people also call it smoking gun for quark plasma because it can provide a calibrated QCD force. Like in the vacuum, we know from the nowadays QCD study or from quite long ago, a very simple Conner-like potential can well describe their vacuum spectroscopy. But when we put it into a thermal medium, once there's temperature or chemical potential, basically, nothing can happen to weaken the interactions between them. And besides, from the model analysis, we also know it will appear, there will be a thermal wave appearing. So reflected in the potential, it's a virtual part will be there. And this is related to the Landau damping or the color object to singlet transitions. But anyhow, once we take such a non-relativistic potential picture for that, we can very simply use such a reduced two-body Schrodinger equation to a Boltzmannian bond state. And within this Hamiltonian, once we put in this complex valued potential, then we are able to convert it into their complex valued eigenvalues related to their spectroscopy, including the mass and also their thermal weight. So now in lattice QCD, people released some results for the Boltzmannian's spectroscopy and different temperatures up to, so I think this is for 5 states of them for the Boltzmannian. The question is, based upon those noisy measurements, are we able to reconstruct their corresponding potential, the immediate ultimate? So this is again an inverse problem, because once we know this complex valued interaction, we can solve this Schrodinger equation, get their corresponding mass and the thermal weight, but based upon some finite measurement, not for the complete set of the Hilbert space, are we able to extract some effective interaction for the Hamiltonian? So this is the inverse problem, and we constructed such a sketch, so such a flow chart to solving this inverse problem. We utilize the deep neural network to represent the interaction. We mentioned in the beginning that deep neural network is a very good, it's a universal approximation, so you don't need to worry the representation ability. You know that there will be a setup for the neural network to very good approximate the underlying potential. You just need to find a way to tune the parameters there. So we use a network to represent this complex valued interaction, and we combine it into the Schrodinger equation solving. Each of the network structure, including the parameter, to the corresponding mass and thermal weight for different Boltzmannian states. So we can compare those results to the lattice released numbers and use the difference to be our loss objective, trying to tune the parameters there. And to perform such an optimization, we can invoke the Hellman-Fermat theorem. Basically, this is telling us some small change of the interaction will induce what kind of change for your eigenvalues, right? You know how to calculate this Jacobins, and you input it into our parameters optimization. In the end, you repeat such a procedure, trying to let your network to really accommodate the lattice QCD result. That's a very natural idea. But we need to validate it in some simple situation first. For example, here, we provide only 5 eigenvalues for such a very simple harmonic system, quantum system, and trying to see if it's able to reconstruct the original harmonic potentials. And this question itself is actually quite interesting, that can we reconstruct Hamiltonian out of some limited spectrum, very similar to the question, can we hear the shape of a drum by our very limited frequency acceptance, right? So here we need to validate it first. So we apply the mentioned flowchart utilizing deep neural network. And in the beginning, our network's representation, we purposely made it to be such a linear line to be different from the ground truth. Then we open the training, so you see the network represented potential will gradually going down and bend itself. And all those change, the information is coming from only these 5 numbers, the 5 eigenvalues, the 5 lowest lying states measurement for that. And in the end, the network into such a state, the represented potential is reproducing quite well the ground truth. But you see some deviation happens for the large distance. And this is also making sense if you invoke this Hammond-Feldman's theorem, saying the information of the Hamiltonian in that range, in the large distance range, is not influencing your 5 lowest lying states anymore. So all the results here are making sense. And we also apply such a strategy to the in-medium stage. And we try to ask about the temperature dependence for the potential as well. So we manually, we call it a closure test because we manually set in such an interaction with this temperature and the radius dependencies. Schrodinger equation, and at different temperatures, it gets the spectroscopy, including the mass and the thermal weight. We put those finite, the limited spectrum as the input to our pipeline to see if we are able to reconstruct back representation for this potential with this temperature and R dependency. So on the right, you see here the reconstruction for the radius dependency and the temperature dependency, and different here. This is at different readers. And to be noted, the temperature values here are different from the temperature values that we provided to such a pipeline. So it's agreeing very well to the ground truth. The solid line are the ground truth, and the dashed curve are from the DNN reconstruction. And on the bottom, you also see there, so the up panel are the real part and the virtual part of the potential for their radius dependency at different temperatures. Bottom panel are the real part and virtual part for the potential at different temperatures, and the values here are different radius. Of course, we see a little bit difference. The band here are quite larger for the very low densities, making sense. If you look at here, that the wave functions of different states, their coverage for the very low distance region is also very small. The information there is not that incorporated. Good, so with those well validated, we apply the same pipeline into the real lattice QCD results. And on the left, you see the reproduction ability of our calculation. So basically, the box is the lattice result, and the open symbols. Open symbols means this different without the filling. This is from the perturbative relation for the potential. So we assume some screened format utilizing the Hahn-Thermal loop expression to be our potential to see how it works in reproducing those results. So we see those open symbols. They can only reproduce well the mass values, but their thermal widths are not reproducing quite well. So the solid symbols, that's the DNN reconstruction, and we see it can simultaneously fit the mass and thermal widths, and in the end, the chi-square per data is on the order of 1. So that means your reconstruction is reasonable. And on the right, you see their temperature and the radius dependency. And interestingly, if we look at the real part, if we increase the temperature, the screening effect indeed can happen, but it's very tiny compared to a lot of the perturbatives that would give us a very different picture in understanding the in-medium Boltzmannian states. We need to change our previously people believe it's a screening dominated picture. Now we need to make a much more dynamical picture in understanding. And we also apply very similar idea into the spectral function reconstruction. So in lattice QCD, people care how to convert your numerically emulated correlators or propagators to their functions. And this is also one inverse problem, but it's a well-known ill-posed inverse problem because we need to explicitly put in the price. So here we utilize the neural network to represent the spectral function and apply this a very simple propagators calculation, apply the Kellen-Lemon kernel here, and you can get their corresponding propagator, and those propagator is supposed to be provided from the lattice calculation. We want to know what kind of spectral can accommodate this lattice measured propagator, and we just tune the parameters of the network represented spectral function. In the end, you repeat such a procedure converge. And of course, you need to introduce some prior information. And there, what we introduce is the smoothness, because essentially we analyzed what's the origin of this ill-posedness. We find that if you take this Kellen-Lemon operator key to be just an operator, you solve the eigenvalues for that, you will find it's having some arbitrarily small eigenvalues. And those were corresponding to some null modes. Null modes is needed in, those null modes will make your inversion operators to be having some arbitrarily large eigenvalues. And this makes any small noise in your correlators measurement to have a big influence on inversions for that. That's the reason for this ill-posedness. So usually those ill-posedness will make, for example, people usually use the maximum entropy method to do this reverse, and you will have some small peaks appearing in the low frequency range for your spectral function. So we introduce purposely the smoothness, trying to regularize such kind of small peaks. In the end, here shows you our reconstruction utilizing the is agreeing quite well with the manually setting ground truth spectral functions. We'll also apply them to some thermochronos, which is mimicking the lattice Qcd case, and we find that it works well with the natural functions situation, also works quite well to this thermochronos applications. And I will skip this slides. This is also a very nice application. So quickly go over this neutron star equation of state reconstruction. I think Kenji explained a lot for that yesterday. And I just want to show you similar strategies using deep neural network can be applied with the automatic differentiation approach to reconstruct the neutron star equation of state. And here on this flowchart, we introduced two neural networks. One neural network is mimicking the TOV equations solving, so this can convert any equation of state to their corresponding mass radius relationship. So this can be well trained per supervised manner. So once you train it very well, you can test it on very different equation of state. Then you just perform a variation input. The input is the equation of state. You try to tune the input to let the outcome to fit our measurement for the mass and radius. So that's a very natural idea. Just for the input for this equation of state, we are introducing a separate equation of state to represent it. And again, for the closure test, we have a very good performance. So the ground truth represented as this blank curve, and the reconstruction with uncertainties represented. And on the right, this is the mass radius relationship. And those blue points is our randomly selected points around this ground truth mass radius curve to be our input for such a fit. And we see that within some uncertainty, our reconstruction can well reproduce the equation of state. And if we apply this strategy to the real data, this red band is our real state. And here, this is for the mass radius. So you can read out what's the corresponding maximum mass for the neutron star, which is around 2.2 something solar mass. Convert them into the tidal deformability and the speed of sound. So that's the result here. And interestingly, for the speed of sound, there's also the peak structure appearing, which is kind of the balancing point between the density part and the very high density parts influence from such a reconstruction. So let me summarize. So basically, machine learning techniques can provide us some toolbox in looking at least here, I showed a lot of the inverse problem solving. So you can either take it as an inversion mapping learning problem, or the statistical fitting problem, or you use the automatic differentiation to explicitly fuse your physical priors into this fitting procedure. So you can try it for your problem that you are interested in. I suggest you, if you are interested in reading out more details within our recent review paper just published this year. So thank you very much.
Thank you, Professor Hello for this nice lecture. And yeah, due to the time limits, a lot of stuff has been skipped. It's quite a pity. And but I think we can have more discussion during the break. And I think since we have already also discussion during, let's have a short break, 10-minute break, and then we come back. And if you have questions, you can come to the stage and discuss with Kaizhou or this afternoon. Okay. Let's thank Professor Zhou again.
Thank you. Thank you for your time.
Our second lecture this morning will be given by Professor Zwilling. Let me first briefly introduce him. Dr. Zwilling is a professor of physics at East Carolina University. He received a bachelor degree in theoretical physics from the USTC in 1990 and a PhD degree in theoretical nuclear physics from Columbia University in 1996. After working at IBM, TAM, OIT, he took the position at ECU since 2007. His main research interest lie in theoretical high-ion physics, radiation physics, and pseudo-CT generation. He's famous for the development of molecular transport model, especially the MPT model, one of the most popular transport models in high-energy high-ion physics. I think many students benefit from this model, including me. He has published more than 100 articles and received more than 6,000 citations. He is also such as the excellent scholar teacher award at ECU. Professor Zwilling will give his lecture about transport model for relativistic heavy-ion collisions. Let's welcome Professor Lin.
I need this, right? Is it turned on? Okay. Thank you. I thank the organizer for it. It's a great pleasure to be here again. So I'm going to talk about transfer model for high-energy nuclear collisions. Here is my outline for the two talks. First, I will give an introduction to models, and then I will use AMPT as the example. So I will show you the structure of the multi-phase transfer model, and then I will show some selected results from the model, including the parton cascade model used in the AMPT model. And the selected results also include a detailed discussion. So I will show some selected results, multiple of them, old results, some very new results. But I mostly show them briefly, but for one of them, I will show in detail. And that is the discussion on escape mechanism. Finally, I will conclude by looking at some challenges and opportunities for transfer model approach for relativistic heavy-ion collisions. So as we know, major goals in heavy-ion physics include the study of the phase diagram, like shown here, and the phase diagram. We want to know the structure, the critical point, whether it exists, equation state, and the deconfinement. We also want to know the QGP properties, such as transport coefficients, viscosities, and the thermalization of different flavors. We want to study also the confinement transition, because you can count, and of course our collisions will go up first, and some high energy collisions will cross boundary and then come down. So for modeling, we need to address both the transition going up and the transition coming down. For the transition coming down, and that is hadronization, and we have to, and that's of course that's confinement transition, and there are different models to do that in hydrodynamics or in transfer models, for example. And then in the research area such as heavy-ion physics, we typically will find surprises, and there are indeed many surprises. For example, vorticity, polarization, spin alignment. Also, people are looking actively at chiromagnetic effects, although it's inconclusive. But people are trying, and we look forward to new results. And also, people are looking for effects from electromagnetic fields created by the high energy collisions. Now, transfer models have been developed for a long time, and they are used to simulate and study heavy ion collisions, nuclear collisions, and for high energy heavy ion collisions, they are developed more recently after or shortly before Rick started in about 20 years ago, 2001-ish. Now, they can be classical transport, and they are mostly based on the Boltzmann equation, or people are more now interested in quantum transport, for example, how to transport spin, how to study the transportation of spin degree freedom or chiral transport. And in this summer school, several previous speakers have talked about these like transport formulation, types of transport, for example, from Professor Hou Defu and Zhuang Pengfei, Lin Shu, and Liao Jinfeng in this school. So here I'm using the Chinese order of the names, as you can see. Now, classical transport models, they are already multitude of these classical models. For example, here I list a bunch of them. As you can see, for example, the top, I guess mouse is better. In the top, you have hadron transport models. They include, for example, the ART model, hadron string dynamics model, URKMD, a SMASH model developed recently. And then there are also several types of parton cascade models. For example, ZPC or MPC, you see PC means parton cascade, and they are both elastic parton transport models. AMPT, called A multi-phase transport, has multiple phases. In particularly, it refers to the parton phase and the hadron phase. So it has parton transport and hadron transport. Currently, the parton transport is only for elastic parton scatterings. And then there is a PASIA, which is similar. It is a hybrid, is a multi-phase model as well. It's parton transport as well as hadron transport. And then there's a BANS, which is a parton transport model, but it includes both the two-body interactions and the 2-to-3 body interactions, and the detailed 3-to-2 parton interactions. And then there's a PHSD model, which is also containing the parton transport and hadron transport, but is using different way to model the parton phase, especially. So here in this list, I have not included event generators that have no secondary interactions. For example, there are many event generators. Most famous ones include PCA and Hygiene, and they are event generators so that they also describe the hadron collisions from the beginning. You give the energy and the beam, projectile and target, then it will give you all the final states particles. However, they don't secondary scatterings in either degrees of freedom, so I do not include them in the transport model here in this talk or in this list. Also, there are many hydrodynamics models, or more realistically, the hydrodynamics models coupled or followed by hadron transport, and they are hybrid models. There are several of them, and we know that they are very successful for describing heavy ion collisions, especially large. And they are also not included in this list for per se the transport models. So from now on, I'm going to use the AMPT model, one of them, for illustration. So I would like you to show you some features of a classical transport model and what's involved the components and what you would need to model, etc. AMPT model is a kinetic theory-based model, so it's based on the Boltzmann equation, essentially, and it aims to provide a description of all the important stages of high-energy heavy ion collisions. So you have projectile A and target B, let's say, and then we will generate, in any kind of multiple phase model, you would generate the initial condition, and then you have a partonic stage, which you describe with, for example, parton cascade or some stochastic parton transport, and then they will hydronize, go through the hydronization process, and in hadron cascade, and then after that is finished, in principle, at the end, after a long time, then you get all the final particles. So this 2004, and it's available online. And their original detailed description is in this reference. And then recently we have written a mini review the recent developments in the mostly in the last 10 years also. What do we need to model to have a comprehensive simulation of heavy ion collisions? Describe the initial particle production or energy production deposition. We would need to take care of the pre-equilibrium interactions in the case that the produced matter is not immediately thermalized. It may take a while, maybe, or maybe it doesn't thermalize at all. So that's a pre-equilibrium stage. And then if it thermalizes or come close to equilibrium, we can use like hydrodynamics to describe the space-time evolution of this near equilibrium QGP. So by QGP here, I mean near equilibrium quark-gluon plasma. And then QCD phase transition by hydronizing the parton degree freedom, and then you go to hadron interactions. So for each stage, you could have different ways of describing it. There are already multiple models typically for each stage. For example, for the initial particle production, there can be the model that includes both soft and hard components, meaning they have the process in addition to description of non-perturbative process. For example, PCA or hiding model, event generators. Or there are also other models like pure soft models, Lund fragmentation, pure PQCD-based models. For pre-equilibrium interaction, then one needs the kinetic theory-based transport models or kinetic theory, solver. Parton cascade includes ZPC or inelastic bumps, for example, and then for the space-time evolution of QGP, once it's near equilibrium, you can also use parton cascade because transport models they do not assume. Although they do not assume the matter is in equilibrium, but if it's near or at equilibrium, it still works. So you can use that. Or it's probably more efficient or advantageous to use ideal or viscous hydrodynamics in that case. Then for hydronization, there are models to convert degrees of freedom from high energy density to low energy density. There are Cooper-Frye, typically used for hydrodynamics, or there's a quark coalescence model developed over the last 20 or so years. And there are also fragmentation, which are important for typically for high energy partons, or now in the language of QGP, maybe if you have partons that cannot do coalescence, cannot find a suitable partner, one partner or two partners, then they have to go through some kind of fragmentation or collective or independent fragmentation. And then for hadron cascade, hadron interactions, typically people use hadron cascade, and there are also several of them, as I mentioned in the previous stage. And for AMPT, we, when the model was constructed, made the choice of choosing the green components in each part as the components so that we connect them and we add the missing information so that we can model each stage. So here is the structure of the first version of the AMPT model, which we call it the default version. And now we use hygiene model to model the initial condition. And this is the two-component model. It has a mean digit for the hard part. Once the momentum transfer is above a certain PT scale, then it's modeled by perturbative QCD as the hard component. And then the rest is modeled by strings, by excited strings or woundings. And then there are typically always some spectator nucleons. Even if you have a central collision, there are some uninteracted, so they will not, they will, typically people think they just don't interact at all, but here in MPT, we allow them to enter the hadron stage, and maybe they occasionally have some interaction with the hadrons that appear at the end. And then the hygiene model is doesn't have all the information we need, and we need to generate the parton space-time information so that we can do scatterings. And then we will, after that, we can do parton cascade in the ZPC model. And then when partons freeze out dynamically, when they no longer interact, then they will go to hydronization through the Lund string fragmentation, which I will show in some detail later. And then hadrons are formed. Initial hadrons will go through hadron cascade, and then we will typically, for hadron cascade, it will take a certain amount of time for it to complete all the hadron interactions. However, because there's at high energies, there's a large Lorentz boost, so the dynamics at large rapidity will take a much long time, very long time. And if you care about time, if you need many events, you can't run to the last interaction at all rapidities. So typically you cut it off at some global time, so that, for example, if I only study near mid rapidity, then I can afford to cut it off at early time, etc. And then after that, you with strong decay all the remaining resonances, rho, mesons, K stars, stuff like that, and then you will get final particles. So here is a animation of a real event from the AMPT model, the default AMPT model, and this is the beam axis, as you can see. So beam axis is into the screen or out of the screen, and so that you have two nuclei, gold nuclei, center aligned, so central collision. And now I will play as function of time here. So time starts here. It starts at almost 0 time, and then at this almost 0 time, you see that this first frame, you see that right after this primary collision, which is assumed to be time 0, you only have some spectators around the periphery because we only plot the formed hadrons, the formed particles, and due to uncertainty principle, any new production of particles takes a finite time. So at time 0, you have the uninteracted incoming nucleons. So some of them may be coming into the screen or out of the screen. I didn't label. And then if I play it, you will see the production of the particles and the transverse expansion. And the left side shows the number of particles. For example, this green line is number of rho, and this line is the pi meson divided by 5, number divided by 5 in this event. And you see the gluons in the red line, they are labeled red here. You see the gluons here, and you can see they're produced and then hydronized quite early. So if you evolve the system to 30 Fermi in the global frame, then in the transverse plane, they arrive at this stage. So you can see the rho decay and increase with time, etc. And I also plotted the kaons and anti-kaons, etc. So if you look carefully, these animations are available at the MPT website. If you look carefully, you can see that if I play it again, and if you follow the time, you can see that at 7 Fermi at middle right, there is a rho decay. It's hard to see in real time. And then if you look at the lower right, there is a anti-K star, which is labeled by this color, and it is produced. So you will see a new color particle, this color particle at 16.6. It vanishes at 20.8 Fermi in the hadron cascade. Yeah. What's that? Yeah, here in the default version is mostly gluons due to the cross. So I labeled gluons as red. So this is the transverse plane. And then we can go to the other direction. So we look at the transverse plane. We can rotate and look at the in this way and look at the longitudinal direction for the same event at 200 GeV. And then you can see, okay, the spectator nucleons, they are, due to the Lorentz contraction, they are very thin in the Z, in the horizontal direction. And then you can see the production of the gluons right away. And then you can see that at 6 Fermi, the middle part are free of gluons, right? The gluons are here at large rapidity. And this is the time dilation effect. And then from the left, you already can see kind of the lifetime of the gluons for all rapidities. So if you play it, then it looks like this, and the middle will hadronize the gluons or hadronize to different hadrons, different color hadrons, and then the dynamics at large rapidity takes a longer time. Then eventually all of them will hadronize.
Is it using PQCD cross-section for partners?
Yes, I'm going to mention that yes, using the PQCD-based cross sections. The formula is based on QCD, but the value is arbitrary. It's controlled by a parameter, by the screening mass. So that is the first version of AMPT model that we constructed. However, soon afterwards, we realized that maybe that model is not good for high energy collisions such as RIC. At that time, RIC has not started really. And the Biot formula, energy density formula, which we all know and love, to estimate the energy density. And then you can easily estimate that, using some parameters or expected energy production per rapidity, and taken the area of the nucleus, gold nucleus, and this proper formation time of partons, let's say, or particles. If we don't know, we'll just take 1 Fermi, typical value for estimate. Then you will find that at RIC or LHC, even SPS, central leg collisions, at about 17 GeV, the energy density is much higher than the QCD phase transition density, which is typically on the order of half GeV per cubic Fermi. Therefore, how can there be the wounded nucleons in the dense area and survive, and how can there be only gluons in the middle but other hadronics degree of freedom like the strings? So it's clear that the strings as a hadronic degree of freedom should not exist at early times in the collision. Instead, we should create a dense parton phase. So then to the string melting version of AMPT model, which we did, if you look at the transverse plane again, now this is non-central collisions, so two gold nuclei side by side, offset in the center, and then you can see that here color coding is so that the blue are the nucleons, uninteracted nucleons, and then the red are the diquark from the string, diquark end from the string, and the black dots are the quark end of the strings, the excited strings, and then the gluon mini jets are the green. So the gluons are considered to be partons, and they are in the middle as expected. Also the excited strings, right, near the middle. And in the default AMPT model, only the green are taking part in the parton cascade. But I mean the red, most of the red are also in that region. Of course, this is a transverse view over all the longitudinal directions, so it's not cut. But you can see that the red are mostly also in that overlap region. That's why those nucleons are wounded. So the idea is this energy density should be high enough so that we should convert these excited, interacted nucleons into parton degree freedom. So that's what we did. And then the structure of the model will become different. So we will have both the mini-jet partons plus the excited wounded nucleons or the excited strings, and we will convert in some way. Idea is to convert all the energy in these two partons, and so that they can rescatter. And the spectator, the blue symbols before, they should all still be hadronic degree freedom. And then after we have these partons and they freeze out, stop interacting, we will have to consider the hadronization scheme to form hadrons properly. So and in the so-called string melting, mini-jet partons is also part of what excites the string. So we melt the strings into partons. Specifically, we let the strings first fragment according to the fragmentation function, so that we have the hadrons that would be created if strings fragment. And then we decompose each hadron according to its quark model content. So that now we go to the other extreme. Almost all gluons, we have all quarks and no gluons due to this scheme of string melting. So we have quarks and antiquarks. And then we will use quark coalescence to do the hadronization. Because once you have quark antiquark, it's natural to do that. And also, if you do that, then if there were no interactions, you recover the hadrons from string fragmentation, and that's what you want as the limit. So here is a view, another animation of the same event in the string melting model. When we do that, then you can see that, let me see how it works. So right away, you see that there are a lot of partons, and here label the red are the quarks, and this kind of color are the antiquarks. So you see, we create a lot of quarks and antiquarks. They occupy basically the middle. This is central collision. On the periphery, there are already some hadrons, as you can see, but in the middle is dominated by partons. And then the system will evolve. And of course, when partons cannot interact anymore in this dense matter, they will that parton will freeze out, and the freeze out is dynamical. So each parton freezes out at different place, different time, according to its future. And then you can see that gradually the matter becomes hadrons. and at 30 Fermi, you still have a lot of quarks, antiquarks in the middle of the transverse plane. But this is kind of misleading because these are the high rapidity, ones. This is a projection, right? So if we go to the other view, the rotated view along the beam axis, then you can see that, because here you can see antiquarks are produced all over the place, and in the middle they freeze out. So here time is 5 Fermi over C, and then it will freeze out after quite some time. And then now at 11 Fermi-ish, you see that the middle is filled almost all with hadrons. And here is time evolution of the quark number, anti-quark number. You can see that it takes, some number of Fermi for some of, a lot of them to hadronize. And the quarks, they coalesce in this picture into hadrons, according to nearby neighbors, and then this matter will expand like this. And you can clearly see the time dilation at the end of the rapidity spectrum. Right. So in this picture, because of the way of melting of the strings, we don't have gluons. And that is, of course, that is unrealistic at high energies. And that is one way to improve the initial condition. So, I think it's pretty clear that there is a big difference between the default version of the MPD melting version, and in the string melting version, there are many more partons, and the parton stage is, of course, more important, and also as a result, the hadron stage starts later, right? Because of the later partons. So then we can look at the individual components of the MPT model. So I already said the hygiene model is used for initial condition. Then the parton cascade includes elastic collisions. Only hadronization is done differently in different models. In the default version, we use the Lund string fragmentation, although there is some parton interactions. And in the string melting MPT model, we use quark coalescence. And then in the hygiene, we include secondary interactions or hadronic interactions of these particles only. So the list is not very long. In principle, one needs more resonances of particles. Of course, it's a job to do that, right? One has to do it one by one explicitly. So right now we have interactions for these lowest, lower mass mesons or baryons, and then all the particles with a PCA flavor code, basically all the particles will be formed because PCA form them, and also quark coalescence are allowed to form all possible particles in the table. However, they just don't have secondary hadron interactions. For example, the public MPT model will produce D meson, strip side, bottom, etc. This is the lag hadron degree, hadron interactions. However, if they are formed by coalescence, the parton interactions are already included. So we can look at more detail about individual components. So for the initial condition from the we have the hygiene model, which goes through Lund fragmentation and produce a bunch of hadrons. And they are the hadrons that we melt. We melt according to the quark model content. Then, as a result, a meson will go to a quark and antiquark. And we label them so that Qm means a quark from the melting of a meson. And a baryon will be decomposed to 3 quarks, and so we can label it as Qb, so it's a quark from the melting of a baryon, and then antibaryon similarly. And we know that actually this string melting process will introduce additional fluctuations to the initial condition. Already there are initial condition fluctuations and there's typically called Monte Carlo Glauber fluctuations in the nucleon interactions and the positions, etc. And then, but each primary nucleon collision is different in PCA if you produce particles. And also, once they produce particles, string melting convert them into partons, so that there's a random nature of the decomposition which introduces additional fluctuation. And also, because we melt the string, we don't only consider the wounded nucleon itself. We let the wounded nucleon fragment according to its, environment mass, etc. So a wounded nucleon will produce. Wounded nucleon is considered to be at the same one transverse location, but it has a longitudinal length in the rapidity, right? In the momentum space. So when it fragments, it will produce a string of flux tube of particles, and then through melting, it will produce a flux tube of partons. And then but the string lengths are fluctuating, and so that will lead to correlations of parton, so-called event, the planes of the different orders of flows, and for the same flow, it will lead to longitudinal correlation or decorrelation of the angle because of the random nature of the string. About the second part, parton cascade, ZPC, it's used to solve the Boson equation. And here, because it only solves two-body scatterings, so the Boson equation can be written this way. And it depends on the cross-section and parton distributions. And for the cross-section, we base the cross-section on the two gluon elastic scattering, cross-section in leading order Qcd. So leading order Qcd gives you this expression. And if you look at the high energy limit and also small, you realize that the dominant cross-section, the cross-section itself is dominated by the forward angle terms, these two terms. And then because of symmetry, you can write it in terms of 1 over t squared. However, one can easily see that if you integrate this for t, gluon is considered to be massless, so you will get divergence. So the small angle scattering is divergent in the total cross-section, and therefore one needs to screen it. And actually, in finite temperature QCD, it will be screened, as we know. However, at that, so here we just add a screening mass, by screening mass mu to the t variable. T for students, that these are the Mandelstam variables, STU, and T is the two-parton is related to the scattering angle of the two partons. We replace T by T minus mu squared here. And then if you integrate it out, you will get the total cross-section. And now in AMPT implementation of AMPT, we add another term, which is mu squared over S. S is again the two-parton central mass frame squared, energy squared. So that, if you integrate this, you don't get A. But we change 1 to 1 plus A, so that after integration, your cross-section is independent of this S. In other words, independent of the two-parton collision energy. Then it's more convenient in phenomenology. Then we can say, what's the how many millibar we are using for the cross-section. Otherwise, it depends on the individual two partons. So that's what we chose to do. Therefore, in the parton cascade, the cross-section is proportional to 1 over mu squared, and this parameter mu is input parameter in the model, which people can vary freely, and so that controls both the magnitude and the angular distribution. Details about parton cascade. Parton cascade solves the two-body scatterings in this ZPC code, and naively the cascade solution, meaning that two particles are allowed to scatter once they are close enough so that they come into the cross section of each other. And this cascade solution is only accurate when the density is low for dilute systems. So naively, one can write a ratio, we call it opacity chi, which is the ratio of the range of particle interaction. That's defined to be root of sigma over pi, right? The range, if I convert cross section into a circle, that's the radius. And then R divided by the mean free path lambda. So if R is small, so that's a dilute system. And if you convert, it's related, this parameter, opacity parameter, is related to the cross section and density of partons. So when chi, this opacity parameter is smaller than 1, qualitatively, we expect the solution to be accurate. If it's much higher than 1, there could be problems. Or in general, there will be problems. So that is called the causality violation in the cascade solution of Boltzmann equation, the relativistic Boltzmann equation. And that's the case for both ZPC and MPC. In general, for parton cascade. Now, and then it's known how to cure this problem. It's by the so-called test particle method or the parton subdivision method, because proposed a long time ago. And this is because this Boltzmann equation is invariant if you do some transformation. If you multiply f by a factor L, but at the same time decrease the sigma by L, to be exact, you should decrease not sigma, but the angular distribution of sigma, d sigma dt, by L. Then the opacity, then the Boltzmann equation is invariant. So it's described the same system, but the chi parameter, the opacity parameter, is lower by a factor of root L. So this L is called the subdivision factor. And so we said that if your system is dense, high chi, but for low chi, we expect the solution to be accurate. Therefore, you just use a large L so that your chi value, new chi value will be lower than 1. And then you expect your solution to be accurate. So that's then you will recover the solution of the Boltzmann equation. However, subdivision method is very time consuming because you increase your particle number by a factor of L, and then you do two-body scatterings, then it squares itself, etc. So it takes more time. And also, that's not the problem for us. The biggest problem is once you do this test particle method, then it alters or destroys completely the correlations between the particles, because these particles are artificially introduced. So, as we know, event by event fluctuation and correlations are very important, especially for small systems. Therefore, we do not prefer this subdivision method. So it will be very desirable to have a parton cascade do this, but still reproduces pretty accurately the solution of the Boltzmann equation. Now let's look at component 3, which is the hadronization in the AMPT model. And as we said, there are two versions of AMPT model that I'm going to cover here. The default version of the model will have the mini jets and the excited strings, and they complete string. And then the mini jet partons will go to ZPC, and then they will be scattered. Because we only have elastic scattering, so they don't change their flavor. They only change their momentum and space coordinates. And then, so an easy way would be to put the same scattered mini-jet into the same string, and then use Lund fragmentation to do hadronization. Because otherwise, it's more complicated. Because otherwise, if you, in general, right, if you have eventually you will have mini-jet quarks. You have also mini-jet quarks, anti-quarks. If your string has a U quark and then you put a D quark there, then the string doesn't have the integer number of it may have fractional charge if you put several partons in some string. So to guarantee the success of string fragmentation, we use this prescription for the default model. But for the string melting model, we use coalescence, as we mentioned. So in the original algorithm of coalescence, quark will start to search its nearby location and find the nearest antiquark to form a meson. The nearest antiquark can be anywhere, coming from anywhere, and then it's space. Yeah, but in the the central mass frame of the two partons. And then and after that is done, we baryons and antibaryons, and for baryons, so you search the quark list, and then the quark from antibaryons will find the two closest quarks, and then they will form a baryon. And same for similar for antibaryons. So this is the algorithm, and then that pairs them right into 2 or 3, and then the flavor is you also need to worry about the hadron flavor, and because of the limited particles. So for example, U bar D, if I find a D quark and the nearest is U bar, and they will form a meson, and then we only have available pion, pi minus or rho minus available, and then we have to decide how to distribute them because they will not form the pearl mass. So we have to decide. So basically, we let the lower invariant mass pairs to form pion and the higher ones form rho meson.
So the chance to find 3 partons at the same station definitely is lower, much lower compared to 2 partons.
So yeah, that could be the case, especially maybe with dilute, right? Yeah, so that's why you see here we force them, right? Kind of. So we let the quark melt from mesons to form mesons, and quarks from baryons form baryons in this way. So that yeah, so that problem will not happen, fortunately. And then for the U bar U quark, then it's more complicated because you can form more. In our list, you can form pi 0, rho 0, eta, or omega. And then we have to deal with that. So for example, then we already know, right, the charged pion and rho this way in the first step. Then we assume that the pi 0 number is the same as the average charged pion number. Then we form that number of pi 0. And similarly for rho 0, and then there will be still more UU bar or DD bars. Then we form eta and omega. So that's what's done. And then this limitation, we force, right? We force meson quarks from mesons to form mesons. Of course, that is the only algorithm. That is not very physical. More recently, we have developed a new algorithm of quark coalescence, so that we allow a quark a freedom to form either a meson or a baryon. So we do it this way. So a parton, let's say we have a quark, any quark in the system. The quark will find the closest antiquark, and then that will be its candidate for forming a meson. And then this quark will also search nearby for two other quarks, and then they could be combined into a baryon. And then we look at the distances for the meson formation in the central mass or the baryon formation. Compare these two distances. So in principle, the closer, the smaller one wins, right? So we do that. This way, then the quark has a freedom to form either meson or baryon, and this is physical model. And also, there is a parameter to control this ratio, because it's not necessarily that the closer will win. Maybe there's a ratio, so we put a parameter to control this. So the parameter will control the anti-baryon to meson ratio, basically.
Are there different mechanisms for the baryon coalescence that you first allow, for example, diquark states, then can find closest one proton to form baryon?
Right, one could also do that way. Yeah.
Because otherwise, this will make the meson and baryons ratio to be largely determined by the phase space in the matrix.
Yeah, so that's why we have this ratio. We put in this parameter so that if naively, right, if the meson distance is smaller than the baryon distance, I form a meson. It's preferred, but we put in the quality equation, we put in a multiplicative factor to control. Then you can control the baryon meson ratio this way to describe the data. So that's an easy way to do it. And also, if you do it this way, then the model reproduces much better the anti-baryon to baryon ratio, as we have shown in this study. So in the old coalescence model, the anti-baryon to baryon ratio, especially for the strange baryons, you see anti-omega to omega or anti-lambda to lambda ratio are from the old model shown by the dashed lines. They are wrong for gold-gold or lead-lead collisions compared to the symbols which are the data. So with the new coalescence, we don't tune it, right? We don't have parameters to control these individual particles, but we have one overall parameter to control the overall total baryon to total meson ratio. And then we describe the data much better. So again, yeah, because I guess this scheme is more physical.
Where did it come from? Because you have exactly as many at the LHT. There are as many quarks as anti-quarks, right? So how, even with the wrong algorithm, I don't understand how we can have a factor of 2.
Yeah.
Preferring anti-baryons over baryon.
Yeah, not for all baryons, right? Otherwise, you would have this problem. But these are the the strange ones. So if you sum over the anti-quarks, etc., then they're still fine. But just the proportion to the strange or anti-strange are wrong, and then the most the anti-nucleons are the majority. So then, let me then talk about the final component, the hadron cascade. The hadron cascade model in MPT is based on the old ART model developed by Bao-An Li and Qiming Ko. And that model was developed for low energy, very low energy nuclear collisions. And then and then later on, the group realized that is missing a lot of the relevant interactions. For example, anti-kaon interactions. Because if you only care about very low energy, there are no anti-kaons. Then you don't care. But once you have you model the high energy nuclear collisions, hadron phase, then you must need that. So gradually, people add more and more interactions and particle productions to the model, to the hadron cascade model. For example, here anti-K-ion interactions are added, and then K0 productions are modeled in the hadron cascade, including nucleon anti-nucleon annihilation, like PP bar annihilation. Then we generalize that to baryon anti-baryon annihilation, and also add a K star meson explicitly as a resonance particle. And then later on, we added eta meson interactions, phi meson, and also production channels for these strange baryons, and also deuteron interactions and productions. So here I will briefly show there are many the channels that we have to include in the hadron cascade. For example, meson-meson channels, right? Meson-meson interactions. There are these SU2 meson interactions like pion, rho meson interactions, etc. Eta meson scatterings, and then channels with strange like pion, SU2 meson can interact and produce KK bar, and also the K star, K bar, etc. All these strange production, and also phi meson interactions. So phi meson we know phi meson of course decays to KK bar, but phi meson can interact with a K bar, and then you get a K-ion out, etc. And then there are meson-baryon channels. For example, K-ion, anti-K-ion nucleon can collide and produce lambda, or the other way, right? And then baryon channels like nucleon interactions and productions of resonances, baryon resonances, and then finally anti-baryon channels like baryon anti-baryon annihilation into mesons. Can be multiple pions, and we model them by modeling, because the two mesons can each be a resonance, like rho or omega. So if you produce 2 rhos, then it's like equivalently 4 pions. So we have added these channels with detail balance, and that's what it takes to address the hadron cascade part. So I think 11:50, so 1 hour. So is that a good time to stop? Yeah. Yeah, let me stop here then.
Okay, thanks. Thank you for providing this nice lecture, and then the time open for questions. And anyone has question, can we ask?
Do you also have mean field?
In the hadron cascade, you mean?
Yeah.
We have, but in the current MPT in the current public MPT model, turn on. So it's not on. However, we have recently another version of MPT which addresses very low energies, and there we made the necessary modifications to turn it on. So for very low energy collisions, we can apply the mean field. Even the momentum dependent mean field, as Zhou Kai mentioned.
Are there any questions for Professor Lin?
I have a very general, maybe philosophy-related question that I'm also quite asking myself. We have 3 words. Sounds like one word is about realistic calculation. One word is those phenomenological transport different version simulations. One word QCD. So how we can maximize our ability speaking to some other words, trying just based on some play around with your preferred words. Do you have something to comment?
So
it's definitely not so realistic, also not such how we can get some stuff to the other world by this world.
yeah,
Yeah,
I think yeah, I will briefly mention some, but it's a very brief. So yeah, it's better to discuss here. For example, yeah, there's something can be done to bridge the world of let's say, for example, parton cascade and QCD. Here, it's very roughly connected right now because it's connection to the gluon PQCD cross section, right? But we take it as a parameter. However, there's a better way. For example, we could actually, I'm right now working on improving the ZPC parton cascade by including all these two-body scatterings, you know, quark, QQ bar to GG, or etc., using the cross-section that's provided or motivated by the finite temperature QCD theory. So we would screen it with the proper screening mass in the derived QCD, finite temperature QCD, and then then do that in the parton cascade. And then you see, then one thing we have to do is we have to know the relation between the you know, what's the cross section we need. We already know that finite temperature QCD, like the Amy theory, if you use it to finite temperature, you know, TC several times above, is not accurate numerically. It's very viscosity is much higher than preferred by experiments or Bayesian analysis. So, but first we need to know the relation between shear viscosity and parton cross sections. We do parton cross sections. However, we don't get viscosity directly from it, right? So we need either to numerically calculate it, but better to calculate it analytically so that we know the relationship. Once we know the relationship and we have these more realistic parton interactions based on finite temperature QCD, then we can adjust the, you know, parameter. It's not based on a dynamic or theoretical model, right? So we cannot say. However, baryon to antibaryon ratio, it will be no problem because, for example, because in either this new coalescence model or the old coalescence model, net baryon number is conserved. And so, going to low energy is basically your net baryon is becoming more important. So you will have P bar P ratio decreasing with decreasing energy. No matter what, if you use reasonable parameters for this coalescence parameter, you will get that just because of the net baryon conservation. Of course, the detail, right, the trend will be correct, and the detail, quantitative detail will depend on the parameter value.
So is there any work on the low energies, any simulations or any comparison between your theory and the experimental data?
At low energies? Yeah. You mean how low?
For example, at start energy scan energy, for example, from 7.7 to 27.
Yeah, I think we have some comparison, but not real comparison. We have not done systematic comparison to BS energy data, but some study has pushed the calculate. It's not a calculation about comparing global observables like multiplicity, PT spectra, etc. But for example, for the when we calculated vorticities in this transform model, we have pushed down to, I think, 39 GeV, and I guess we pushed down to some other energies, but in overall is okay because we have done systematic study when we improved. I'm not going to talk about the recent improvements of the model, but recently, recent means 5 years from now already. We have improved the model by updating the PDF, the nucleon PDF distribution, and also nuclear shadowing in the hygiene model. And there we did a systematic study of PP and AA collisions from throughout different energies. And there we, global observables seem to be fine. Yeah, but not at, it depends on your quantitative accuracy which you are aiming for. If you are looking at high accuracy comparison, then we have to do it.
Okay, thank you.
Question? 其他的什么？
Whether the full momentum is conserved in the coalescence model?
Yeah, that's a good question. In the coalescence model, either the new or old one is not conserved because we are coalescing. You know well, right? We are coalescing two particles into an on-shell particle with the pole mass, so it's not conserved. And we know about it when we did this, and we checked the degree of violation. So in the model, we for momentum conservation, but one of them we can choose to satisfy 3 and violate 1. So we chose to conserve the 3 momentum, and then the energy will be violated somewhat.
So the full momentum will be conserved in the process.
No, the four momentum, you mean the 4 components?
3.
Yeah, 3 momentum is conserved, but not the energy.
Oh, the energy conservation
is broken. Yeah.
Yeah.
Yeah, people have studied the effect in the early days about this.
I would like to know in your AMPT model, can you compute the yields of deuteron or triton?
We did a deuteron yield study. Actually, in the, I think I showed this one. Yeah, we put in deuterons and we look at deuteron production there. But for triton, we don't, because here the deuterons are we add the deuteron production channels into hadron cascade. For tritons, you have to do the same explicitly, so we have not done that. And here it was done a long time ago, and recently, people realize that there are additional deuteron channels that could be more important. So, yeah, if you want to quantitatively study deuteron production, then this should not be accurate enough. But nowadays, people often do hadron coalescence or a model after transform model. For example, you can use MPT and get the final state particle, including the baryon, proton, nucleon, space-time information, momentum information. Then you can put a coalescence model on top of that to produce heavy nuclei, including triton or even heavier ones.
Any more questions? I don't see any more questions. So let's thank Professor Lin and Professor Kai for their nice lectures. And we will meet after afternoon, 2 o'clock.